welcome to Chapter 18. We are still talking about circuits, but now we'll be talking about resistors in series and parallel. So what we're going to do is we're going to calculate equivalent resistances for circuits in series and find the current and potential difference across each resistor. And then we're going to do the same thing for circuits in parallel. So when we talk about series, okay, what that means is it's any set of resistors or light bulbs, or really any load, that have the same current through them, okay, and this means that they have to be on the same path. If this is true, they're said to be in series. So an example of what that might look like would be something like this. If we have a battery, and it goes around, and we have this resistor here, and one resistor here. Okay, in this case we only have one loop. Right, so if we call this one R1 and R2, then we'd say that R1 and R2 are in series, because there's only one path for the current to flow through as it goes around. Okay, and they're on that same path. We can also have resistors in series, even if there's other loops in the circuit. So if we had an example like this, where we have one resistor here, and then we have two here. Okay, so if this is R1, R2, and R3, right, we still have the current that goes around this one, right? So that one's not in series with anything, but we can take the ones that go out and around here. These two, R2 and R3, are on the same loop, so these two are still in series. With series, we can also calculate the equivalent resistance of resistors in series. An equivalent resistance just means the resistance needed to replace all the resistors with one resistor, right? So if we took our example with the two resistors, right, okay, and then we turn that into something that is going to be equivalent. So if this is R1 and R2, okay, then we would turn it instead into something like this, where we just have one resistor, okay, and this is the equivalent resistance. Excuse me, that should be a Q. Okay, so when we do that for series, equivalent resistance is really easy. Okay, so we write it REQ. Okay, I don't know why I keep writing G's, sorry about that. Okay, let's make that a Q. And that will just be equal to the sum of all the resistors. So R1 plus R2 plus any other resistors we might have. Okay. So we're going to do that for a practice problem now. So we're going to draw and calculate, okay, the equivalent resistance of a circuit containing a 5 ohm resistor and 12 ohm resistor in series connected to a 9 volt battery. Okay. So all we need to do is let's look at our original circuit. Okay, so we have one resistor, two resistor. Okay, one is 5 ohms, the other is 12 ohms. Okay, so we use our R equivalent equation, which means we just add them up. So our equivalent is just going to be 5 ohms plus 12 ohms, which gives us 17 ohms. Okay, so then we draw our new equivalent circuit with one resistor, and I forgot to label the volts, with 17 ohms, and this is our equivalent circuit. Okay, so this circuit and this one have the same resistance, even though this one has two resistors and this has one resistor. So one thing we also need to notice is that in series circuits, the sum of voltages across each resistor in a series is equal to the total current of the circuit. So what that means is if we take this, and I'm going to take the circuit we were just looking at, okay, but I'm going to move the resistors so they're in one line, because it's easier to see and understand this. Okay, so here we have our 5 ohm resistor and our 12 ohm resistor. Okay, and we know that gives us a circuit, sorry, my lines are not very accurate on this, right, of 1 with 17 ohms. Okay, so if this is 9 volts here, and it's plus and minus, there's going to be a voltage drop across of these, and it's going to be opposite, okay, so that it like cancels out. So we'll have V1, and then a V2, that drops across each resistor. Okay, and that will be equal to the 9 volts. Okay, so the total voltage, V total equals V1 plus V2. Okay, and in this case, that's going to be equal to our 9 volts. So how do we find that? Okay, well, we need to use our equivalent resistance circuit. Okay, because that allows us to find the current through each one. Okay, and then once we find the current, then we can go ahead and use Ohm's law again to find the voltage in each of these cases. So we're just going to do that right now. So first we're going to use this one. Okay, we're going to come down here, and we know that we can use our V equals IR, except we want to use the I version, which is V over R. Okay, and so then we plug in, we've got our 9 volts divided by 17 ohms, so our current here is going to be equal to 0.53 amps. Okay, so now all we do is we're going to take this information and we're going to use it with these, and we're still going to use V equals IR, but now we're going to find it for each one, and they should total up to 9. So as we do this, we're actually solving for V, so we can just leave it in this equation. Okay, so V1 will equal our current times resistor 1, okay, which is going to be 0.53 amps, times our resistor 1, which is 5 ohms. Okay, and that will tell us that V1 is going to be 2.6 ohms. Okay, now we can also do the same thing and find V2. So V2 equals IR2, which is 0.53 times 12 ohms this time. Okay, and that is going to equal 6.4 amps. And now if we check, 2.6 plus 6.4 is indeed 9. Okay, so we did get everything working out right. So you can see that the voltage that drops across both of our resistors here does end up being the voltage of that. So now we're going to move on and talk about parallel resistors. So any set of resistors that have separate paths for current. So this is the opposite. Before it was the same path, okay? Now this is separate paths for current, and that means they have the same voltage across each, okay? So these are said to be parallel. So what that looks like in a circuit is if we have a battery, right? And then we plug a resistor across it, and then we need a separate path. So we're going to have a resistor here, and really we could keep going on forever and ever, okay? But here if we've got R1 and R2, R1 and R2 are in parallel because they have separate paths for the current to flow through them. Okay. So we can then and see what the equivalent resistance for resistors in parallel are going to look like. Okay, so this equation is a little bit more complicated. We can't simply add them up. Okay, so remember for series, right, our equivalent was just R1 plus R2 plus any other resistors in the series. Okay, so I want you to also notice here that when you do this, that means our equivalent is always going to be greater than any other resistor in the series. Okay, it's always going to be bigger. So now if we look at resistors in parallel, the equation for that is 1 over our equivalent equals 1 over R1 plus 1 over R2 plus on for however many you have. Okay, so if we solve for our equivalent, what that means is we end up with our equivalent equals 1 divided by 1 over R1 plus 1 over, whoops, let's try that again, 1 over R2 plus any of the others. Okay, so this is the equation then that we can use to solve for the equivalent resistance of resistors in parallel. So now we're going to calculate what the equivalent resistance of the circuit would be if we had those same two resistors we had before, right? The 5 ohm resistor and the 12 ohm resistor with a 9 volt battery, but now they are in parallel instead. So the circuit we're starting out with looks like this, right, where this is 5 ohms, and this is 12 ohms, and we're going to find our equivalent resistor, and what its equivalent resistance will be. Okay, so we need to use our new equation. So R equivalent equals 1 divided by 1 over R1, which is 5, plus 1 over our other one, which is R12. So if we take that and we plug that in into our calculators, we find out that it's going to be 3.6 ohms. I want you to notice here that this 3.6 is less than either 5 or 12. Okay, so for parallel, our equivalent is always less than any of the R values. Okay, it will always be smaller. So that's a good way to double check what's going on. Okay, so now that we have this, just like we talked in the other one, we can also find the current. Okay, so in parallel circuits, the sum of the current through each resistor in parallel is equal to the total current of the circuit. So what that looks like is if we have our circuit here, okay, with our resistors, right, we're going to have a certain current that's going through this one and another current that's going through this one. And we'll have the total current that enters both of these, okay? So this I total, we call this I1 and I2, okay? The total current will equal the sum of each current through each resistor, okay? And if this was others, we could add this dot, 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 okay? So we're just going to take a look and see if that is true really fast. And again, like the other one, we need to use our equivalent, okay, in order to find it. Because what we have to do is we have to find the total current. So we use our equivalent circuit, which we know. Let's just draw it really fast. Okay, where our equivalent is that 3.6 ohms we just had. And this is 9 volts. So using that, okay, we're solving for I, which will be V over R. So we're going to end up with 9 volts divided by 3.6. Okay. And that ends up coming to 2.6 amps. Okay, and so now we can find these I1s and I2s to see how that goes. Okay, so going back up there then, right, we know that this is 5 ohms and this is 12 ohms for our resistor. Okay, so plugging things in, we're going to get that I1 equals V1 over R1. And here the voltage across each of these, one of the things about a parallel circuit is if this is 9 volts, that means this resistor has 9 volts across it and this resistor has 9 volts across it. So 9 volts, 9 volts, 9 volts. As long as there's no other resistors up here, we know that it will always be this way, okay? So that's one of the characteristics of parallel circuits. So here we can plug in 9 for V. So going back to that, then what we do is we've got 9 volts divided by our 5 ohms, and that gives us 1.8 amps. Okay, so we can kind of guess what the other one's going to have to be to add up to 2.6, but let's see if we can get that. So I2 will be V2 over R2, which is still 9 volts over 12 now, which ends up coming to 0.8 amps. And in fact, if we add them up, 0.8 and 0.8, we get 0.6, and then we have a 2 over here, so 2.6 amps, and they do match. So that is what we want to get. Alright, so that brings us then to the end of our series and parallel circuits. You'll get plenty of chance to practice this in class, and I'll see you guys there.